Jonathan Fasano, and together we make up Iradion's Laser Simulation and Optimization Development Team. This project is quite different from the other projects you've seen here today, as instead of requiring a background in computer or electrical engineering, it asks for a background in physics and mathematics. We both chose this project due to the challenge it imposed, and today we're here to show you what makes this project so unique compared to the others. Iradion is a company that creates carbon dioxide lasers, such as their Infinity Series model depicted on the slide here. The beam is emitted with a wavelength of 10.6 microns, which is outside the visible spectrum of light. These lasers are used globally in many different applications and in many different facilities. The inside of this laser has a laser cavity that looks something like this. The cavity consists of two mirrors, spherical mirrors of slightly different sizes. These mirrors are positioned off-center from one another and at a distance so that their focal points converge at one specific location. When light moves between these two mirrors, the smaller mirror magnifies the light to the point where eventually some of it will escape through a hole cut above the smaller mirror and emit as a laser beam. These features are what make up a negative branch confocal unstable resonator. Now, despite how often they're used in the laser industry, carbon dioxide lasers aren't actually very well modeled. As such, whenever a company like Iradion needs to make changes, they have to do so manually. Every time they want to try new sizes or new measurements of components, they have to replace them and then put back their previous measurements whenever they don't work. If the company had a simulation that could simulate these changes and laser outputs without them having to implement these changes manually, they'd be able to save time and money that they lose every time they had to make one of these changes and be able to put it elsewhere. This is where we come in. We have been tasked with mathematically modeling this laser cavity in MATLAB. One of the biggest differences between modeling a laser and actually measuring a physical beam is determining the beam quality and spatial distribution of the laser. Normally, you can fire a laser beam into a beam profiler like the one depicted here to get these measurements. When modeling a laser, you have to take measurements at different times and distances from the apparatus as it is cycled. This is something we'll go into in a bit more detail on later in the presentation. In addition, we were also asked to make this program robust so that it can control and change various features that the company wants to look into. When we entered this project, we came up with a sort of game plan and how we wanted to tackle every step in the process. In order to do anything at first, we needed basic laser physics and optics research to be done, along with reorientation of using MATLAB as a software. The step after this was to begin modeling basic laser outputs. These would start very simple and eventually evolve into becoming full-blown laser systems. The next step is to model the resonator itself. Once the model is complete, the next step is to tune the laser alongside the actual beam. The model would need to be accurate and deemed passable before it could go on to the final phase, which is to create a graphical user interface and an instruction manual to make the software easier for the company to use. Jonathan will now go into more detail on the project's current technical accomplishments and what remains for the project to come.
So, our research began looking into laser and physics. Initially, we looked into understanding laser theory, as well as the specific cavity that Iradion wants us to model. We spent the majority of our time, however, learning about light propagation and its behaviors in three-dimensional free space. Additionally, we had to be able to represent this light mathematically so that we can model things in MATLAB for future simulations. Our first assignment in MATLAB was to generate a plane, seen on the left here, and propagate the electromagnetic light wave for some distance in free space. After doing so, we would sample the field's intensity. This is what it looks like propagating through. After doing this system, we had a basic overall template for all of our modeling systems going forward. Each week, we added additional system elements, such as apertures, lenses, and mirrors. It got more and more complex each week. However, by adding in these elements, we introduced diffraction into the system. Simply put, diffraction is when light is incident at the edge of an object that causes it to bend. The resulting waves interact and cause constructive and destructive interference. This interference directly impacts the intensity profiles. For short-range propagation distances seen here, we can see that this intensity profile has a broad distribution and chaotic fringe pattern. This is known as near-field intensity distribution. As we increase our distance, however, and get sufficiently far away from the source of diffraction, we see a far-field intensity distribution, which is characterized by a smooth, concentrated Gaussian beam. This is the ideal laser output beam. We then tried to verify this in MATLAB using a rectangular aperture. As seen here, we have the chaotic fringe pattern in the near field, and as we progress along the axis for further distances, we see that the chaos smooths and eventually converges to the expected far field intensity distribution. The next and most important step was modeling the actual laser cavity. We started looking at just a generic laser cavity. In this case, the light will bounce back and forth, and each iteration, some light will escape through the partial reflector. For modeling purposes, we convert these mirrors into ideal convex lenses and maintain the aperture for the exit light. We then use a process called unfolding the resonator, which is to take this two lens system and adapt it to a periodic array of ideal lenses. The light will then propagate through, and we expect that the longer it propagates through, the more and more ideal and Gaussian the output beam will be. We can use the escaping light to verify this, as it's indicative of the state of the intercavity light for that given point where it's sampled. These intensity plots display that the beam distribution over time indeed will converge to our target output of a concentrated Gaussian beam. Once this is complete, we will begin to tune this model with the actual data from the lasers at our Iradion facility. When this is successfully finished, we will then develop a graphical user interface for Iradion employees to use and provide ease of use. We want to thank everyone that helped us and supported us in this project.